Welcome to a video on section 3.4, derivatives as rates of change. Okay, we're going to be talking about the Kentucky Derby. The winner of the 2025 Kentucky Derby was a horse named Sovereignty. We don't know who the jockey was. Nobody cares about that. Who finished with a winning time of 2 minutes and 2.31 seconds over the 1 1/4 mile track. What was the average speed in miles per hour of the horse? So I did a little bit of work ahead of time before I started today, and I converted the 2 minutes to, as you can imagine, 120 seconds. That's 60 times 2, and then I added in the extra time for a total of 122.31 seconds, and I took that to minutes by dividing by 60, and then I took that finally to hours by dividing by 60 again. So dividing by 60 twice gave me this really small value, and then with that work done I could figure out, okay, well, if the horse went 1.25 miles, because that again is the 1 1/4 mile track, and the horse did that in 0.033975 hours, if you divide that, you get the horse had an average speed of 36.8 miles per hour. Pretty fast, almost as fast as I can run. Very, very fast. Here's a picture of Sovereignty crossing the finish line. You can see the white post is the finish line. The question is, how fast is the horse going in the picture? Well, yeah, of course it's a trick question. At first, the obvious answer is like, well, 0, right? Because the horse is not moving. Once you take a picture of something, it's not moving at all. But that's also not a very satisfying answer, because it doesn't make sense that we would tell a story and say when the horse crossed the finish line, it was going 0, because of course it doesn't move at all if it's doing that. So what happens when you take this picture of it is that the horse is no longer traveling anywhere, right? It's going 0 miles, and time is also stopped temporarily, so it's doing that in 0 hours. And if you think about what we have here, we have this 0 divided by 0 situation. It's that indeterminate situation we've talked about before with limits. So 0 miles per hour is definitely not a good answer and makes no sense in the real world. What we really want to do is we want to shrink the frame down so small that we can get a sense of what that instantaneous rate of change is crossing the line. That's our derivative, and so we would use that 0 over 0 concept. But for a minute, I'm going to go back and talk about this rate piece here in general. Let's take a look at an average rate of change in general. So in this box here, what you see is I have a definition for the rate of change. The rate of change is a comparison of two units, and it's often change in something per change in time. Here's a couple examples. I just did miles per hour. It could be feet per second. It could be meters per minute. It also doesn't have to be a measurement of distance. It could be something like if I'm making donuts, maybe I make 12 donuts per hour, or that seems kind of slow. How about 12 donuts per minute? That seems kind of fast. But anyway, it's a rate of something per time. It doesn't have to be time, but generally a rate, we think of it as time. So here's a generalized version of the whole thing. If we have a function defined over a given closed interval, the average rate of change can be thought of as the slope between the values. Notice that here there's a definition and an equation, which is the change in the function value for the change in x. That might seem very familiar, like change in y over change in x. Hey, that looks familiar. That's my derivative. That's my slope of a line in general. And the formula should look very familiar. It should remind you of back in the algebra course, y2 minus y1 over x2 minus x1, just really finding the slope. But we're using function notation, and so we do f of b minus f of a over b minus a. What that's basically saying, if we have a point a comma f of a, we might have another point over here that's b comma f of b. Then if we want to find the average value, we would think of the slope of the line between those 2 points. That would be our average rate of change between those two. Now, what we don't know is if we only have 2 points, we don't know that it traveled in a straight line. It might have in fact been a curve along the way, but we know that the average overall can be calculated with the slope of that line. Let's take a look at a real-life example, or at least a pseudo-real-life example. We talk about a car racing around a 1 mile track here. Now, if a car's going around a track, you might think the laps are probably fairly consistent in time, but not exactly. So let's see what I mean here. So one lap took 40 seconds. By the time they finished the second lap, that was 1:18. But if you went back and just doubled 40 seconds, you could see that would actually be 1:20. So it appears that the second lap was even faster. The third lap took another 32 seconds or something. So not all the laps are the same rate. And what we want to know for question A here is, what is the average speed in miles per hour of the car over the first 10 laps? So if we want the average speed, we don't have to use the formula from above, and we'll do that a little bit later in the video, that f of b. But for now, let's just think about it as, okay, if we know how far the car went, right, that is the number of miles, and we divide it by the number of hours, then we're going to know how fast the car went. Well, what we know is that each lap is exactly 1 mile. So if 10 laps took place, that was exactly 10 miles. And it took 6 minutes, 5 seconds. So I have a little bit of work to do there, right? 6 minutes, 5 seconds. Nope, didn't spell that right. If we convert that to minutes, 6 times 60, 360 seconds there, and then I add the 5, that would be equal to 365 seconds. Now, since we want miles per hour, we're going to have to convert the 365 to seconds. I'll show you a way that I learned back when I was in high school in a physics course. So if you're a STEM major taking physics or chemistry, this might be a very familiar way to do it. You don't have to do it this way, but this is one route. So you could just take that number and insert it here. But the problem is we want miles per hour, but we have miles per second. So you just multiply by your conversion factors. So there would be 60 seconds in any 1 minute, and that makes seconds go away. And then you know that there are 60 minutes in any 1 hour, and then the minutes go away, and there you would have your grand total answer. You would have 10 times 60 divided by 365. I have a calculator on hand, so I'm going to use that. 10 times 60s divided by 365. I'm getting 98.63, approximately 98.63 miles per hour. So we can say that that's about how fast the car went, or that was its average speed over the 10 laps. Of course, it doesn't mean that the car always went 98.63 miles per hour, like a cruise control. That's just the average. B, what is a good approximation of the instantaneous velocity? Now, that's our derivative. That's like that snapshot of that horse crossing the finish line that I showed you earlier. 4 minutes into the race. So if we go up to the table and we were just maybe highlight that box, 4 minutes into the race. Oh, I'm sorry, that's 4 laps. Let me erase that. We're looking at the 4-minute mark, so we got to look at the minutes. Okay, well, we don't exactly have that. Notice this is 3 minutes 37 seconds. This is 4 minutes 10 seconds. So somewhere inserted between these two would be the 4-minute mark. Now, there's no way we would know exactly how fast the car was going right then because we don't have enough data, and that's why the question says, what's a good approximation? Well, what we're kind of asking here is, I'm going to write this in, is the velocity at time 4, and so we're going to get at it by saying it's approximately equal to, using the points around it, we're going to use the f of b minus f of a approach to estimate this, knowing ahead of time that this is not exactly the answer. It's our best estimate. So if we look around it, what are the two values, mileage changes around it? Well, that would just be lap 7 versus lap 6. So it's going 1 mile between these two data points. I'm highlighting these two pieces of information because the 4 minutes falls between it. And then if I look at the elapse in time, that's the bottom there, right? I have the 4 minutes and 10 seconds, subtracting the 3:37. So let's see where this takes us. All right, so what we can see is that we have 1 mile elapsed there in that amount of time. So I did a little bit of work to myself, but I realized that this is 250 seconds. And 3 minutes and 37 seconds is 217 seconds. And if you subtract those, you should get 1 mile in 33 seconds. But again, we want miles per hour, so we're going to do that same conversion of 60 seconds for every minute. And again, we're going to do 60 minutes for every hour. I'm going to use a calculator to approximate this. So we got the top 1 times 60 times 60. We're going to divide that by the 33. And we find that the car has a little bit faster average rate between those two, 109.09 miles per hour. That's faster than our overall average race rate of the race. So what we find out is like, yeah, you know, in the middle of the race, the car is probably averaging a little bit faster than at the beginning and at the end. So that's what we find out. Is it the exact instantaneous velocity? No, but we're using a best estimate. So what we're going to do is think about narrowing this window to shorter and shorter time frames, and that's what we're going to use the derivative for. Okay, example 2. The population of a town in thousands is modeled by this function. P of t is 2.4 plus 0.075t, where t is the number of years since the year 2000. Okay, so that's key. Find the average rate of change of the population between the years 2005 and the year 2015. So what we're going to do is we're going to set up that basic formula again to think about it, but let's think about the units this time. What is our B and A? What is our F of B and F of A? Now here we are doing a change in time on the bottom because time is elapsing, but on the top, notice that it's talking about a change in population. That's what the function is about. All right, so that's what we got to keep in mind. So let's see. On the top, our population can be calculated in the formula. You know, I'm going to update this. Instead of using f, let's go ahead and use the letter given to us in this particular problem. It says it's a function named p rather than f, but it's the same formula. So we want to know between the years of 2005 and 2010. All right, but notice that it says t. T is the input into the function right there. T is the number of years since 2000. So that means that the year 2005 will correspond with t equals 5 years, and the year 2015 will correspond with the t equals 15, because it's talking about years since 2000. So our b minus a is 15 minus 5. You could have done that in your head, I know, 10 years. On the top, we're going to use our function. What is p of b and p of a? That'll be the p of 15 minus the p of 5. So we're going to plug into this function up there to figure out what that is. You might want to pause the video and try that on your calculator. I'm going to do the same. Okay, I found out when I plug in 15, I get 3.525. When I plug in 5 into the function, I get 2.775. Now remember that this is a, okay, gotta do it right there. This is talking about the thousands of people. So don't think that there's 3.5 people. It's 3.525 thousand people. And so, this is thousands. So let's modify this so it makes more sense. We're talking about 3,525 people, and they're back in the year 2005, there was only 2,775 people over that 10-year span. Okay, so this is people. And so what was our change in people? Let's do a little subtraction. 3,525 subtracting 2,775. They gained 750 people, and they did that over a matter of 10 years. And so if you do the division there, you can see that would be 75 people added to the population per year. All right, so that is our average rate of change for this population. That's how you would use that formula. All right, example 3, I want you to try that. Maybe pause the video here and just use the information given in the problem. Try to apply the correct units as well. And after you've done that, turn the video back on to check your answer. Okay, so you can see my calculations here. H of 6 minus h of 2 over 6 minus 2. All the calculations out. I'm getting a grand total of 58.8 meters per second if I didn't make any calculation errors. Again, remember to apply those units, and you get those units right from the description in the problem. Okay, now let's go back and talk more about that instantaneous rate of change. That's that first question I was concerned with. It was like, when that horse is crossing the finish line and you snap a shot there, how fast is it going right then at that one boom point? All right, so you can't use average rate of change. You're narrowing it down to nothing, so you have this 0 divided by 0 situation. And so we want to recall that our slope is our rise of our run over change in y and change in x. So we're going to be using this notation we're going to be talking a little bit more about as the class proceeds, dy over dx. And that's a natural notation because the delta y is a Greek letter delta. Delta we normally use for change, and the dy is actually in Greek a lowercase delta. So another way to say dy dx using the Greek would sound like delta y over delta x, or the change in y over the change in x. So that's where our notation comes from. So if the function has given units for the input and output, the derivative is going to take those on, just like the examples from above. So let's take a look at those same problems that we looked at, but now instantaneous. So let's revisit number 4. It says the population of a town in thousands is modeled by this function. We used this earlier, where t is the number of years since 2000. What is the instantaneous rate of change? So right then, right now, in the year 2024. So what this means mathematically for us, instantaneous rate, means that we want to know the derivative value at the appropriate year. Now let's recall that this would be, since it's years after 2000, that would be t equals 24. We want p prime of 24, and then we're just going to apply the appropriate units. So what we'll do is we'll use our derivative rules from before. Let's find the derivative first of the p function. So the derivative of 2.4, that's just a constant, so that's 0. The derivative of 0.075t, that's just a linear one, and you can see it's just going to be the slope, 0.05t. Or you could think of using the power rule, bring the power down and reduce by 1. It's just going to be 0.075, and so that will be our derivative. And thus, well, we can simplify that, right? It's just 0.075. And if we plug in 24, well, there's no t to plug it into. It's a constant derivative change. So it's 0.075. Now, remember that this was in thousands. So let's go ahead and change this back to something that makes sense in English. If we, multiply that by 1,000 because it's in thousands, what we'll find is we move this decimal place over 3 times. It is that the change is, is 75 people per year. So it turns out in that particular problem that the instantaneous rate of change was exactly the same if we scroll back up to that average rate of change. And the reason it was is because this function was just a line where the derivative is the same no matter where it's a constant, so it's always the same. Something's going to be different in number 5 because our derivative won't just be a constant. Let's look at this rocket launch. We want to do the same thing. Find the instantaneous rate of change of the rocket when t equals 3. Another way of saying that is we want the instantaneous rate of change, or h prime, when t is 3. So our job will be first to find the derivative function. So the derivative of negative 4.9 t squared, bring the power down to, multiply by the 4.9. I'm using my calculator just to make sure. And it is negative 9.8. That's negative 4.9 times 2. And then reduce the power by 1, so t to the first. Then take the derivative of 98t, and that's just 98. Now we can do the work of plugging in 3. And so we have negative 9.8 times 3 plus 98. And let's see what that is. Let's see, I have 68.6. And then we need to apply the units. The units are given in the problem, meters and seconds. So this is meters per second. What this means for us, like if we think of it, the whole problem, when this rocket is launched at exactly the 3-second mark, we should find that its rate of change is exactly 68.6 meters per second at that one time. So even though I didn't do a limit here because we've figured out how to do derivatives using these shortcuts, very, very handy, we're actually taking care of that 0 divided by 0 situation, and we have this value that we can find at an exact point. Really, really cool to know how fast something is moving at any one point in time. This is a calculus concept. I wanted to give you just a table with some other descriptions and units as possible. These are things that are pretty common to a calculus class that will use s of t as a position function. Don't ask me, I didn't come up with the s, that's just how it is. Don't worry, the next one makes more sense. V of t we'll use for velocity, and I want you to notice that the velocity function is just the derivative of the position function. We're going to talk about maybe why that is in just a second. If you take the absolute value of the velocity function, you get something we call speed. This is going to be described more probably in a physics course. Velocity is tells you how fast an object is moving and its direction. Could be positive or negative. If you have speed, it's the absolute value of it because speed is always a positive number. I'll give you an example. If you're in your car and you're going 60 miles per hour, your speed is 60 miles per hour. But if you put the car in reverse and roll it down a hill backwards at 60 miles per hour, it's still a speed of 60 miles per hour. But if you talk about velocity, you could say that it has forward velocity of negative 60 and backwards velocity of negative 60. So it's a directional with a sign. The acceleration is telling you how much the velocity is changing at any one time. And so the way we find that is we actually can find the acceleration by taking the derivative of the velocity function, which is the second derivative of the position function. Now, if you examine the units, maybe it'll start to make sense of why that's the case. So let's take a look at those units. If our units, let's just focus on one. Let's just look at feet. Didn't mean to do that. I just crossed it out. I was trying to use my highlighter. Let's examine feet. If you take the derivative, and let's say t is in seconds, you end up with feet per second because it's that dy over dx. If you do it once more, you get feet per second because you've done that second derivative, and that's an acceleration feature. So that's why those make sense as a relationship. So we're going to exploit that and look at that a little bit. Maybe exploit is not quite the right word, but look at it. So here I've provided a graph for this story. A ball is dropped from a height of 64 feet. Now, I know that this picture of this graph doesn't look like a ball is falling. It looks like it's being thrown out, but this is not a picture of the path of the ball. What it's doing is mapping the number of seconds versus the elevation. So here at you can see at 0 seconds, at this point right here, at the 0 second mark, it's graphed up at 64 feet. And then later on down here, what this is saying is after 2 seconds, because t is our input, right? That's seconds. We are down at 0 feet. Okay, so that's what's going on there. And anywhere in between, this kind of tells you the position of the ball in the air. Notice that it's kind of speeding up over time. Of course, gravity tends to speed something. So this question is at what instantaneous velocity does the ball strike the ground? How fast is the ball when it hits the ground? So another way to write that out mathematically is v of, well, the time when it hits the ground, and you can see here it's the 2-second mark. So we want v of 2. Now remember the relationship from above, that's going to be the position function's derivative. Alright, so that's really what we're looking for. So what we'll do first is we'll find that velocity function. V of t is s prime of t, and let's take the derivative of this. Let's bring the power down and reduce it by 1, and we should get negative 32t, and the derivative of 64 is a constant, that's 0. So that's our velocity function, and so if we want v of 2, we're just going to plug 2 into that derivative, and we get negative 64. And now let's just apply the units. Alright, now let's apply the units, and we have velocity. We were talking about feet and seconds, so it's negative 64 feet per second. Well, let's talk about the negative. When we're talking about the direction of an object, if it's moving up in elevation, like if the ball is flying upwards, we consider that positive velocity. When the object is traveling towards the earth downwards, that's negative velocity. That's why it has its negative. All right. Of course, its speed would be 64 feet per second, but its velocity negative 64. B, what is the ball's average velocity during its fall? So this is taking us back to that formula right at the beginning. We want to do v of 2, because that's when it hit the ground, minus v of 0 over 2 minus 0. All right, we already know v of 2. It's given as negative 64 in the previous part. And the first one, we don't even need to use the formula from above. We can just even use common sense, like how fast was the ball traveling at time 0? Well, at time 0, you hadn't let go of it yet, so it was traveling 0. Anyhow, you could plug in. And if you just do a little division here, you can figure out its average velocity over the fall was negative 32 feet per second. Of course, its impact velocity was much higher than that. All right, so last thing I want to talk about here is that relationship between those 8 things, the position, the velocity, and the acceleration function. So this one says, it doesn't have a story, right? It's a story about a particle traveling on the coordinate axis. So imagine you have, this coordinate axis, t, and there's a particle moving on there, and sometimes it's moving to the right, sometimes it's moving to the left. This function will tell you where it is at any time. So, for example, if you plugged in 0, you would get 4. You would figure out, okay, when we start, it's at position 4, and then it moves right and left after that, depending on what's happening with the function. So the first question is find v of t. Well, the way the relationship is to get from position to velocity, you need that derivative. So let's find the derivative of s of t over there. Using the power rule, 3t squared minus 18t plus 24. Done. All right. And we know that it will have units if it had given us more information. This is a unitless problem. B, at what time is the particle at rest, meaning not moving? So another way to think about this is at rest means velocity is 0. Okay, so since we have a velocity function from above, this is kind of asking us an algebra question. When is this function 0? Oh, okay, it's an equation. We can solve it. Looks like a quadratic, and notice everything's divisible by 3. So let's factor the 3 out. We have t squared minus 6t plus 8. Keep your fingers crossed that this will actually factor, because if it does, we don't have to use the quadratic formula. And it looks like it does. It looks like this will factor to t minus 4, t minus 2. And so our values are t equals 4 and 2. And so we have 2 answers to when the particle is at rest. We don't know if it's seconds or hours. It doesn't say in the problem, but that's our answer there. Then C, when is the particle moving right? When is the particle moving left? So when something's moving right, we say that it has positive velocity. And when it's moving left, we say it has negative velocity. I want you to just examine this one on Desmos. I'm just going to leave that as an extra activity that I'm not going to examine on this video. But what you can do is you can take a look at this velocity function right here. If you take a look at its graph, you notice that it's a quadratic, so it's going to be something like that. Of course, that's not an exact picture. You can look at Desmos for more. So the positive velocity will be when it's above the x-axis, and the negative velocity won't be when it's below the x-axis. We'll examine that more in class and in future lessons, and that's all for this lesson.